Good afternoon, everyone. Today we're going to start chapter 6. It's going to be related to traffic loading and volume. We know again how important traffic is related to pavement engineering and pavement analysis and design. So, in order to do so, we need to consider traffic from different perspectives. One of them is the loading magnitude and configuration, as well as the number of loading repetitions. So, there is a huge demand and need for a detailed estimation of the traffic loading due to so many factors such as the increased axle loading. The axle loading now that we handle or the pavement on our highway system handles is much more than before, and there is also higher tire pressures. Tire pressures used to be somewhere between 25 to 30 psi, and now we have way higher pressure than this. It's mainly also for the 18 wheelers. We have higher tire pressure, and therefore this is going to induce much more amount of the stresses on the pavement. We also need to be familiar with the new axle configurations. The 18 wheelers, again, they are known to have the dual tires or the tandem single dual tires or but now with the bigger trucks, and now we have what we call the super heavy load trucks. That we have new different axle configurations, including up to 12 tires per axle sometimes. And so we need to know those new axle configurations to include them in our pavement design. As you can see in this picture here, this is the traffic volume. Traffic volume again varies. There is a whole bunch of traffic mix that we can see on any interstate system. We can see from the small vehicles that can weigh 3 to 4,000 pounds, all the way to 18 wheelers that they are about 80,000 pounds, and even more for the super heavy loads that they can range from half a million pounds all the way to 3 to 4 million pounds as gross vehicle weight. And we need to be aware of those volumes in order to design the pavement structure that can handle that much of traffic. The Federal Highway Administration vehicle classification, they have different categories or classification for vehicles. This still need to be updated, but the ones that we have now under FHWA and under the Mechanistic and Empirical Pavement Design Guides software is start from motorcycle, passenger cars, other axle, two axle, four tire single vehicles. We have buses as category 4, all the way to category 13, which we have 7 or more axle multi-trailer trucks. When it comes to axle configuration, these are the typical namings that we use in our pavement engineering community. We have single axle, single tire. As you can see here, we just have one single tire from each side, and it's just one axle, single axle. We can have single axle dual tires, which is this is the typical that we see in 18 wheelers. We can have tandem axle single tires, meaning that we're going to have two single tire axles that they are very closely related or situated compared to each other. That's why we call them tandem axle, and we can have tandem axle dual tires as well. The traffic loading, again, this is here an example for the FHWA class 4, which is a bus, and we can have class 5, which is two axle, still two axles, single tire, and it's a single truck unit. And this is here another example for the class 8, um, which we have now. You could see we have four or less axle single trailer trucks. So we have one in the back, two, three, and four. We can have class 10, which is six or more axle single trailer trucks. Class 11, we have now five or less axle multi-trailer trucks, and all the way to class 13. This is the highest based on the one of the highest classes in FHWA, which is seven or more axle multi-trailer trucks. And the tractor semi-trailer 18-wheeler truck. This is again the typical trucks. Again, they range from small sizes to bigger sizes. Yet again, we have now the new beast on the road, which is the super heavy load trucks, which are again way higher loads. They can go up to 4 million pounds, and the axle configuration is significantly different. We can have again 8 to 12 tires per axle. So, traffic analysis related to our pavement engineering world, pavement structural design does require us to know and quantify all expected loads a pavement will encounter over its design life. So, what are the variables that we need to know for traffic from the traffic engineering perspective and how it impacts our pavement engineering design? We need to know the axle load magnitude. We need to know what's the axle configuration. I need to know what's the number of load applications, the growth rate, whether this traffic amount is going to grow or get reduced with time, the lane distribution, which means how many lanes per direction do I have, and therefore traffic will distribute among these lanes, the tire pressure, again, is it low or high, and of course the speed, as we got to know that asphalt pavement is viscoelastic material, is going to act as a strong material under high frequency, which is higher speeds, or is going to act as a weaker material under lower speeds. So when it comes to traffic analysis related to pavement design, there are three different procedures that we can consider for vehicular and traffic effects in pavement design. The first one is the fixed traffic, the second is fixed vehicle, and the third one is variable traffic and vehicle. So let's start with the first one. A fixed traffic procedure, actually this is now we're trying in this procedure to design thickness determined by single wheel load magnitude independent of load repetition. So here we're looking into a certain wheel that we typically see it repeated over and over, and we try to see that any wheel configuration can be converted to this equivalent single wheel load, which is ESWL, equivalent single wheel load. So the design typically here is performed based on the largest equivalent single wheel load within all the configurations. And this type of method, it's been used mainly for airports and heavy traffic highways, mainly for airports to be specific, simply because if we're having specific wheel from the aircraft that's been used over and over, we can use this wheel as a fixed traffic, and every other wheels, whether they are smaller or bigger, we can convert them to this equivalent single wheel load, and then we may make again we do the design of the pavement for this airfield based on that, but it's not commonly used nowadays compared to the two other methods that I'm gonna show it to you in a little bit. The next method is the fixed vehicle method. So this is here now, it's a design thickness method, which is determined by the number of repetitions of a standard single axle load, which is the 18 kips uh, axle. So this is here, and most this axle is a typical axle for most of the 18 wheelers where we see single axle, and every axle is handling about 18,000 pounds. It's a dual tire single axle, which is two tires from each side. So what we do in this method, actually any axle or wheel configuration that is not 18 kips or consist of tandem or tridem axles is actually now we need to convert it to an equivalent single wheel load, which is the ESL, by multiplying the number of repetitions of each one of these configuration into an equivalent single axle factor. So for example, if I have two axles from my own little vehicle, each one of those axles is handling barely 2,000 pounds, then we need to multiply this axle by an equivalent axle load factor, or EALF, to convert this axle to how much damage that this small axle will introduce to the pavement compared to the equivalent single axle load that is 18 kips. Same thing if I have a super big axle that is handling much more than 18 kips, there should be also an equivalent axle load factor to multiply that axle to convert it to the standardized equivalent single axle load. The third method is actually now variable traffic and variable vehicles. So this is the design now is performed on individual effects on each and every traffic and vehicle that we face in the field. So it's mostly commonly used in mechanistic design approach. For example, the new ASHTO Mechanistic Empirical Pavement Design Guide. It's now, instead of trying to come up with an equivalent single axle load that can convert everything to one number. Now we look into a mix mixed traffic, and we want to see the individual damage that comes from each one of those axles. So there is no need to convert any to an equivalent axle load, and it has been used heavily by the PCA, which is the Portland Cement Association, with some design charts. So the ME design, which is the mechanistic empirical guide, uses the load spectra approach. The load spectra approach is basically characterize loads for single, tandem, tridem, and quad axles, which are directly related to the number of axle configuration and its own weight. So it doesn't involve any conversion, as I mentioned, to equivalent values. And the ESEL approach, which was developed under the ASHTO 1993, is not needed for this analysis anymore. So let's talk about the ESELs, which is again, this is the Merrill method. As I showed you, again, we have the first method, which is the fixed traffic. The second is the fixed vehicle. And the third is variable traffic and vehicle. So let's talk about this one, which is ESELs, which is still highly used nowadays in most of state DOTs around the country. So what is this method also is all about, again, is we're trying to convert mixed traffic into equivalent 18 kip single axis. So the load equivalent factors used for the conversion um, convert any axle to what we call it the ESELs. The equivalent axle based actually on the loss in serviceability measured by the ASHTO test. What does that mean? That means they did, again, as you recall, they did lots of testing on the ASHTO roads by introducing small axles, bigger axles, the equivalent single axle, and then they measured the amount of damage that came from each one of these axles. And this is how they came up with the equivalent single axle load based on, again, the loss of serviceability or the loss or the amount of damage that the pavement experienced by experiencing low axle weight or high axle weight. And then they came up with these tables to help us to convert any individual axle to the ESELs. So what does serviceability really mean? As I mentioned, it's the ability of a specific section of pavement to serve traffic in its existing condition. And to do so, we have an index called Present Serviceability Index. This was developed by the ASHTO road test in order to determine the serviceability, or again, the strength of the pavement at certain time once we establish or once we pave the road. So the present serviceability index is a PSI index. It's actually a mathematical combination of values which are obtained from certain physical measurements. So it's actually formulated to predict the PSR, which is the present serviceability index of the pavement. So the PSR is actually the way it's done. It's an average of an individual rating made by members of a specific panel, and the rating comes from zero start from zero all the way to five. Five is very good or actually excellent, and approaching two or one all the way theoretically speaking to zero, that's a very poor pavement. So for flexible pavement, again, the PSI, the present serviceability index, is heavily based on pavement roughness, how rough is the road, and the distress condition, such as rutting, cracking, and patching. If we have lots of these distresses on the surface of the pavement, therefore the present serviceability index will go low by default. Rigid pavements, the PSI, the present serviceability index, depend on other distresses, such as faulting, spalling, transverse cracks, as well as the number of full depth repairs. So again, the higher the amount of stresses, the higher the more severe are those stresses, the lower the PSI will be for this section. This is here a little schematic that shows you what is the PCI and what's the rating. So this is here, the y-axis is the PSI from, again, as low as 0 and as high as 5. And this is the traffic amount, or actually you can relate traffic to time. As time goes by, how the pavement will react. So typically, a brand new flexible pavement will start from an initial serviceability equal to 4.2. Nothing is perfect, so we don't rate it at 5, but typically a brand new pavement will be rated at 4.2 at the beginning of the once we open the section to traffic, and then with time, as you can see in this graph, pavement will start to degrade until we have maintenance or rehabilitation event where it's going to go up, and then with time again things degrade one more time. So the PI, this is the initial serviceability for flexible pavement, is typically 4.2. For rigid pavement, it is around 4.5. The other question is where to start or how to define a damaged value, or where is now the failure point. The failure point, or what we call the terminal serviceability, PT, it actually depends on the importance of the structure. So if we have an interstate highway, we're gonna call this structure is failing once we reach a PSI, a terminal PSI equal to 3. If it's a highway or major arterial, it's 2.5. If it's a local street, it's going to be equal to 2. So this is again how we define the initial serviceability all the way to the terminal serviceability. So the terminal serviceability, as this shows you here, somewhere between 2 to 3 is failure, depending again on the importance and the classification of the roadway that we're looking at. How to calculate the easels number by itself, the total number of passes of the standard axle load during the design period is defined by this a fundamental equation. The easels, the equivalent single axle load, is actually the summation of all the axle groups from axle group 1 all the way to the axle group number M, which is again regardless of how many axles we're trying to convert. And it's basically the multiplication between Fi times Ni. Fi, this is the equivalent axle load factor for the ith axle group times the number of passes of that ith load group. So basically what we're saying is, let's say I have multiple axles that I observed, and each axle was repeated, let's say n times. So all what you need to do to get the easels for that observation is simply the equivalent axle load factor for this specific axle times how many axles you observed and how many repetitions of that specific axle. And then you're going to keep summing up all these repeated axles times its own ELAF until you get the number of equivalent single axle load. So as I said, this is the theoretical equation, and then now we're going to try to extra derive the equation to have the final equation that we're going to use in our analysis. But just to give you another explanation, what's the ELF? EALF, which is the equivalent axle load factor. Sometimes you see it in other textbook as LEF, load equivalency factor, or F by itself, or equivalent axle ELAF. So regardless of the naming, it's basically it defines the damage to the pavement by any axle load relative to the damage induced by a single standard axle, which is the 18 kips. So it's the ratio. As you could see, this is here the ratio between the number of 18 kip easels causing a given loss or a given amount of damage over the number of X kept axle causing the same serviceability loss. So it's pretty much a ratio that gives us a damage ratio between what would this axle, individual axle, would make much damage versus the damage that could have been caused by the typical 18 wheelers. So let's have an example to understand this much more. So consider that we have two identical pavement structures subjected to loading from two different axle types. So two identical structures, we're going to have two different axle types. One is we're going to assume that the first pavement structure is going to sustain, it's going to handle 100,000 applications of an 18-wheeler, 18 kips, I mean, single axle for a serviceability drop from 4.2 to 2.5. While the second pavement is going to sustain only 14,347 applications of a 30 kip single axle for the same serviceability loss. What should be the equivalent axle load factor? So what are we trying to say here? We're having two identical structure. One is handling 100,000 18 kips a single axle, this is the equivalent single axle load. So it handled 100,000 before it reached failure at 2.5 psi, and an identical pavement section is handled only 14,347 applications or repetitions of the 30 kip. So what would be the equivalent single axle load is typically, as this equation says, this is, we're going to apply this simple equation, it's the number of repetitions of the 18 kips or the number over the number of x, in this case is 30 kip, causing the same serviceability loss. So that's why if we divide the 100,000 over the 14,347, this is now what's going to give us the equivalent um, the load equivalent factor or equivalent axle load factor, which is 6.97. What does this number really mean? It means that the 14,347 passes of the 30 kips is actually will introduce or will produce the same amount of damage as if I have 100,000 applications or repetitions of the 18 kips single axle. Or if you want to look at it from a different perspective, it's actually that one pass of the 30 kips single axle would cause the same amount of damage, equivalent to about 7 passes of the 18 kips. Where did I get the 7? It's actually this number here, 6.97. So roughly 7. What does this mean? That means every one pass of the 30 kip axle is gonna have the same amount of damage equivalent to 7 passes of the 18 kip single axle load. So coming back, so once we now understand what's the ELAF, which is equivalent axle load factor, it actually where did we come up with these factors and how did they come up with these tables that I told you about that the AASHTO came up with? These factors they highly depend on the pavement type. If it's flexible pavement versus rigid pavement, things will change. For example, flexible pavement damage based on 18 kip, comparing it to 30 kip is going to be different than having a rigid pavement handling these same two axes, 18 versus 30. Same thing with thickness. If I have a thicker structure, the experience is going to be different. The structural capacity as well, and the pavement condition, depending on the terminal conditions at which the pavement is considered failure. So because each pavement structure responds differently to any given load, each pavement type or structure will have a different load equivalency factor, and therefore we're going to have multiple tables to look up and use depending again on the pavement type, the thickness, the structural capacity, as well as the pavement condition. So how can we determine the ELAF? It can be actually derived, empirically or it can be derived theoretically. So the way we derive it empirically is actually based on the empirical equations that was developed from the AASHTO Road in 1972. It can also derive theoretically based on critical stresses and strains on the pavements and the failure criteria. For example, I can construct a roadway and then I can apply the certain amount of repetitions using the 18 kips single axle. This is the equivalent single axle, and then I can have an identical pavement. I apply it now with a different axle configuration, different weight. Let's say 30 kip, like what we saw in the example, and then reach the same amount of damage. Measure how many equivalent single axle load repetitions versus the 30 kip repetition and come up with your own equivalent axle load factor. So the empirical way, as I mentioned, was done based on the AASHTO. The AASHTO 1993 equivalent factors. It's actually a regression equation, as you could see, is based on the results of the road test that was developed back again using the AASHTO sections. So this equation came from Huang book. It's equation 6.20 and it's page 257. So the equation, as you can see, is a log of WTX over WT18, and as you may expect, this is here the WTX over WT18. This is the equivalency factor or the ELAF. The weight of any given axle over the weight of the 18 kips is equal to this empirical equation, which is based again on the structure of the structure, the thickness of the structure, the stiffness of the structure, and other factors as I'm going to mention in a little bit. So as I said, that ratio WT18 over WTX, this is the equivalent axle load factor. WT18 is the number of the 18 kip single axle load application to time t, and the WTX is the number of axle load application at the end of that time. And again, it's mainly a function of the PT, which is the terminal serviceability index. What's the failure point, or what's the PSI? Remember that curve from 0 to 5. So what's the PSI at the terminal serviceability um, or the terminal life of this pavement, and the SN, which is the structural number. This is basically an index indicating the overall structural capacity of that pavement. So the AASHTO Design Guide 1993 came up with lots of tables that can provide you with, the ELAF. So those tables of equivalent factors for the structural number values of 1, 2, 3, 4, 5, and 6, and PT values ranges from 2 to 2.5 to 3. So those tables have a wide range of what structural number are you handling from 1 to 6, and a wide range of PT, the terminal serviceability, for 2, 2.5, and 3, because these are the numbers that actually correspond to what type of structure are you handling. Remember, if it's an interstate, it's 3. If it's an arterial or again medium major road, it's 2.5. If it's a local street, it's gonna be the terminal serviceability is gonna be 2. So this is here an example with one of these tables. It's table D1. This is axle load equivalency factor for flexible pavement. And this table is only for single axles, and the PT, terminal serviceability, is 2. So if you're doing, let's say, I-20, interstate I-20 or I-80, you can't use this table. This table is only for local streets or collectors that we designed them at a PT equal to 2. And then here we look into the axle load in KIPS. So, and here we have the pavement structural number from 1 to 6. As you could tell, if you go all the way down to 18, this is the axle load. This is the equivalent single axle load. That's why the equivalency factor is 1, because this is the standardized axle that we try to convert everything to it. But let's say now if I'm going to do the 30 kips, let's say structure number of 4, 30 kips, structure number of 4, so it's 8.6. What does that mean? That means, again, the every one axle of 30 kips is going to have the same amount of damage as 8.6 from the 18 kip equivalent single axle. The equivalent single axle particularly is not sensitive to pavement thickness, and structure number 5 may be used for most of the cases. As you could see here from this graph, it doesn't change that much. For example, if I have structure number 1, 10.4, 10, 9.2, 8.6, 9.7, and 9.2. So typically after structure number 4, 5, and 6, they're about the same. That's why we typically pick structure number 5 as the get-go to use in this table. So unless if I'm mentioning it to you, then you can use the structure number 5 to pick from. And as well, since you also use the AASHTO equivalent factors at PT equal to 2.5 and structure number equal to 5 in most of the structures. Those tables, again, it's in Huang's book, table 6.4, page 259, and also you can find them in the AASHTO 1993. It's table D.4 and D.5 and D.6. So let's have an example here to try to understand how can we use this table. So assume I'm going to have an 18-wheeler. So now basically I'm looking into an 18-wheeler truck, and I want to know how many equivalent single axle load that will come from this truck. So the truck has a truck tractor, which having a steering axle, which is a single axle, which is 14,000 pounds, and it's having a drive axle, which is a tandem axle, and this tandem axle having 34,000 pounds. And then I have the trailer, which is a trailer axle, which is a tandem axle having 30,000 pounds. So those are the 3 different axles that we need to convert to know how many axles that comes from this one single 18-wheeler truck. So if you look up the tables in your textbook, it's going to show you that the total equivalent damage by this truck at PT, which is terminal serviceability equal to 3, assuming it's on an interstate system, and the structure number equal to 3. So the steering wheel at 14,000 pounds is going to be equivalent to 0.47 ESL. And for the drive axle, it's at 34,000 pounds, this is equivalent to 1.15 ESL. And then the pole axle is 30,000 pounds, but it's 0.79 ESLs. Why is that? Because you may ask, how come it's 0.7 now, which is less than an easel, although this is 30,000 pounds. But 30,000 pounds, you need to go to the table for the pole axle, which is a tandem. Tandem, the equivalent single axle for tandem is 18 times 2. So 18 times 2, that's 36. So 30, it explains why the 30 is less than 1 easel. So if you sum up all these numbers, now we're going to have a number equal to 2.4 easels, which means that this 18-wheeler is equivalent to 2.4 equivalent single axle load. So if a pavement is subjected to 100 of these trucks each day in one direction for 20 years, which is 5 days a week, let's say, the total e-cells for this truck would be this much, 1.25 million e-cells. Where did we get this from? Again, if it's 5 days, every um, over 7 days. So there's just a ratio to give us how many days per year we're going to operate this truck times 20 years times 100 trucks a day, and each truck is having 2.4 1 e-cells per truck. We're going to have 1.25, 1 million and quarter worth of e-cells just coming from 20 years application of this truck, 100 trucks a day. Let alone, again, if you have much more than 100 trucks, you could see the number of e-cells can grow pretty drastically. And all this even while assuming that the annual growth is zero, but although traffic does grow with time. I am gonna stop right here for this segment of the lecture, and I will see you and meet you in the next segment of this class. Thank you so much.